Okay, the extended linearity principle, which applies to non-homogeneous equations, comes in two parts. The first part we proved in the last video in the context of linear systems. That's that if you have a linear non-homogeneous equation and you have a solution to that, and you have a solution to the associated homogeneous equation and you add them together, then you have built another solution to that original non-homogeneous differential equation. The second part, we're going to prove that in the context of a second order differential equation. The second part says if you have two solutions to the non-homogeneous linear equation, the difference between them will be a solution to the associated homogeneous equation. So I've got up here a second order linear non-homogeneous differential equation. Now, I happen to have chosen mine so that I've got constant coefficients a, b, and c. I could easily just have changed those to be functions of t. I'd write a of t, b of t, c of t. The statement of the theorem would be the same. The proof would be the same, except that I'd be writing a of t, b of t, and c of t. Okay. All right, so we're going to prove that if we have two solutions to star this equation, then the difference between them is a solution to the associated homogeneous equation. Now, I want to just point out that while I refer to this by name here, it's not written on the board anywhere, so it's not given. This equation is given, the associated homogeneous isn't. That means it's part of my job as the proof writer to explicitly state what it is, and I think I'll start with that. So note that the associated homogeneous equation, what I like to call A, is a d squared y by dt squared plus b dy by dt plus c y is equal to 0. And let's just call that double star, because I'm going to be trying to prove that this thing is a solution to this particular equation. Okay, so we're proving an if-then, so of course we want to suppose the if. So we will suppose that y1 and y2 are solutions to equation star. And as always, once I've supposed I have a solution, whether I've supposed it or claimed it, the next thing I want to do is spell out what does that mean. What it means is that when I plug in these functions for y, I get a true equation. Okay. So then a times d squared y1 by dt squared plus b by dy1 by dt plus c times y1 is equal to f of t. So the left-hand side is just what I get if I plug in y1 and its derivatives. Let's call that smiley face. Okay. And I'm going to write the same thing with y2 plugged in. So a times the second derivative of y2 plus b times the first derivative of y2 plus c times y2 is equal to f of t, and I will call that monster. Okay. So we've spelled out what our supposition means. So our task is to prove the then part. I find it helpful to just write out that that's my claim. It's not absolutely necessary to do that, but I find it helpful because that really gives me a goal to work towards in my proof. So I'm going to say claim y1 minus y2 is a solution to, and it's a solution I'm claiming to the associated homogeneous, which I labeled as double star. Okay. All right, I'm going to spell out what that means. So again, whether I've supposed it or whether I'm about to claim that it's true, getting it into an equation is going to be most helpful. Okay. So I am claiming that a times the second derivative of y1 minus y2 plus b times the first derivative of y1 minus y2 plus c times y1 minus y2 is equal to 0. Okay, because that's the right-hand side of the associated homogeneous. And this, I'm going to prove that it's true. I'm not stating it's true yet. I'm claiming that's my goal. So I'm just going to identify that this is my claim written as an equation. And what I'm going to do is I'm going to simply start with that left-hand side and simplify it and hope that I can simplify it to 0. So if I call this the left-hand side, I can say left-hand side is a times the second derivative of y1 minus y2 plus b times the first derivative of y1 minus y2 plus c times y1 minus y2. Now, that's going to be a times, I know that derivatives are linear. In other words, they distribute over sums and differences. So the second derivative of this difference is the second derivative of y1 minus the second derivative of y2 plus b times, I can use that same property for the first derivative. This is going to be the first derivative of y1 minus the first derivative of y2. And then plus c times y1 minus y2. Okay. Now, I'm just going to use the distributive property. I can distribute the a's, I can distribute the b, I can distribute the c. Okay. So I'm going to have a times the second derivative of y1 minus a times the second derivative of y2 plus b times the first derivative of y1 minus b times the first derivative of y2 plus c times y1 minus c times y2. Now, this was just spelling out my suppositions. I'm going to need that in a moment. So I think what I'm going to do is erase the claim up here and continue my work up at the top of the board. Now you'll notice that I've got 6 terms here. 3 of them involve y1 and 3 of them involve y2. I want to just regroup them. And I can do that because I'm allowed to change the order, that's the commutative property, and I'm allowed to group things in different groups with parentheses. Okay. So that is using the commutative and the associative law together. That's the one time I'm sort of allowing you to use 2 things in one step. Okay. Because just really all we're doing is rearranging things. Okay. So I'm going to say, coming up here, that this is equal to a times the second derivative of y1 with respect to t. And then I'm going to jump to the next term that has a y1 plus b times the first derivative of y1. And then I'm going to jump to the next term that has a y1 plus c times y1. Yes. Okay. And then what's left is all of these terms that have a y2 in them. And notice they all have a negative sign in front. So we'll have minus a times the second derivative of y2 minus b times the first derivative of y2 minus c times y2. Okay. All right, I can factor out that negative sign. So I can say I've got a times the second derivative of y1 plus b times the first, plus b times the first derivative of y1 plus c times y1 minus a times the second derivative of y2, that should be a dt squared, plus b times the first derivative of y2 plus c times y2. But now, what I have right here, well, that's equal to f of t by smiley face. And what I'm subtracting from it, well, that's equal to f of t. And that's by Monster. So just plugging those in, f of t minus f of t is exactly equal to 0, which is what we were trying to prove. So, thus, the claim is true.